since I was surrounded by the medical talks, then let me remind you that my talk is in theoretical physics, in atoms in very strong fields, and let me start. So. The title of my talk is Multi-Layer Polaronic Nondispersing Trojan-Like Wavepackets on Langmuir Type 2 Click-Clack balls trajectories. And in helium atom and quantum dots. Okay, so let me start from the introduction. What are Trojan wave packets, which they appear in the title, and imagine that you have the hydrogen atom, the atom of hydrogen, the simplest atom you can imagine, with the proton in the center, and you put this atom in the circularly polarized laser field or strong microwave field, depends on the scaling of the packet to the radius of the orbit, depends on the wavelength. And you find out that you have solutions of the Schrödinger equation, time-dependent Schrödinger equation, which are simply solitons built from the probability density. Since this conference is multidisciplinary, and there is a probability that people from other fields are also listening, because I was listening to medical talks and I understand them anyway outside. So let me remind you what is soliton. Soliton is a solution of the wave equation, which is simply shape invariant, and the wave equation is normally nonlinear to build a soliton. So this probability density is moving around the nucleus with shape invariance, and these states were discovered by me, Joseph Eberle from University of Rochester, and Iwo Biański-Birula from Warsaw, Poland, which recently was granted the Wigner Medal for these states as one of the many contributions of his life work. And I observed them first on Cray simulations in 1993. This was Crazy 90, so the processor speed was Crazy 90 at the time was equivalent more or less to today's PCs, at least in the sense of this problem, handling this problem. It was bigger, but now you can observe this on PC. The same simulations in 2023. You can 30 years later you can observe this on home PC. So why they were called Trojans? Because they correspond to the problem of the Trojan asteroids, which are moving around the sun, and with the Lagrange equilibrium points created by a system of the sun and Jupiter. Okay, that's why they were called the Trojan asteroids, and this is basically the stability diagram of the hydrogen atom in the CP field in the rotating frame, and you have the blue zones are corresponding to the stable positions, stable motions, and the red zones are to unstable motions. Okay, so you also can look at the problem as the panning trap, and the panning trap is the device invented very long time ago, but the electron is basically Trojan electron. You can consider as trapped by the single electron panning trap. Okay, and with the magnetic field, which is magnetic field, such a funny thing that it is emulating the rotation of the stationary space. Okay. And okay, so you can understand the intuitive in the intuitive picture the stability zones of this kind of Hamiltonian of the harmonic oscillator with the rotation. Okay, by simply adding and subtracting something which you can call the anti-centrifugal potential. Okay, so you add the anti-centrifugal potential is with the sign minus. Okay, and minus is plus. So if you collect these terms, this term which appears in the rotating frame due to the rotation, and collect with the minus simply minus of the centrifugal potential, that you will get the simply the generalized extremum of the wave function in the magnetic field. Okay, so you can explain this in the very, you see this is the exact calculations, and this is the stability diagram based on the intuitive picture. So you can actually see that these zones corresponds to strong maximum, which cannot be stabilized by the magnetic field. These zones correspond to minimum, which are always stable because minimum is doing, and these zones, small triangles, correspond to the Trojan wave packet zones. The intuitive picture is not predicting really the exact zones, because there are some mustache. Okay, here you have mustache here, which are from the exact calculations, but basically the intuitive picture is predicting, and the normal panning trap is corresponding to this square, and strictly the original one for which Nobel Prize was granted corresponds to this fat red line. So in other words, you can look at the Trojan atom in the rotating frame as the panning trap, elliptical panning trap. Normally, original panning trap is cylindrical, but you can consider elliptical, that it's squeezed like the car muffler. Okay, normally, and this corresponds to elliptical, and also Trojan wave packet in some sense also. Only the maximum, which is stabilized by the magnetic field, is much stronger. Okay, so now let me go further. You can also look at this as a stroboscopic picture, blur vision stroboscopic picture, that the saddle point is rotating, and it is the plane x equals 0 and y equals 0 are drawing one-dimensional curves, simply parabolas, and these parabolas are rotating, and they are drawing paraboloid, two paraboloids. Okay, and if you want that you want the coefficients of these two be larger than 1. That's how you predict this picture here. Those two triangles, which are essential for Trojan stabilization. Okay, now there are critics of the harmonic theory that it is too. It works only for very small laser frequencies, or electromagnetic field. we build the nonlinear theory, which says basically that if you expand those states in the basis of the hydrogenic eigenstates, you obtain that they are pendular states of there are grand states of the pendulum, which with the negative mass. Okay. Now we extended these two circle trajectories. Okay. Here are it is a page of the Langmuir paper from 20s last century, and he discovered that you can actually put two Trojan electrons on two Bohr electrons actually, because he never considered in the fields. Okay, on two parallel trajectories, and I call this Hooperings configurations because of females Hooperings. Okay, and now you put these trajectories they are originally unstable, so you put them in the combination of magnetic field and perpendicular to the plane of motion and the CP field rotating in phase. And this is my physical review letter about it. And here also again the transparency when you can solve the problem, and you do classical stability analysis, basically known from physics handbooks, and you see that if you perturb the original trajectories, that they are flowing away, they are unstable, and you must add magnetic field and CP field. This is stability diagram as a function of the this is in units when the magnetic field is either +1 or -1 only, the magnetic field term, and this is the x-axis. The x-axis is the frequency, and the y-axis is the electric field. Okay, so you basically this is how they look in the Monte Carlo simulations. This is the movie. Okay, so there are two electrons moving on two parallel circles. Okay, and now here is the movie. Now let me skip this. Okay, you can do simulations using a quantum density functional theory, and you can extend this to many electrons which are frozen. This is in rotating frame. Electrons are frozen in the rotating frame, and they are simply if you went to rotating frame, it's a frozen configuration of electron resembling molecules but built from electrons simply. Okay, and now we wanted to go beyond this static picture in the rotating frame, and we now use the trajectories which I call Click-Clack Boltz trajectories. Okay, because they also invented by Langmuir in 20s. And this is the popular toy. So you know, if you look at this toy and you know this toy, you know how they are working. They are simply bouncing up and down. You make the hand motion up and down in the middle of the string, and you put the balls to collisions. That's why I call them the Hamiltonian scales. Okay, you have scaling by if you scale the size, you scale the frequencies. This also you can extend to quantum dot. Here is the potential external. This was a spherical quantum dot with the external harmonic potential. Okay, and now these are the trajectories when they are not focused. The initial condition is not prepared precisely to click-clack, so they are oscillating, and this is what happens if you make the small kick perpendicular to the motion of the previous paper, previous slide. Okay, and now this you can focus them actually. So electrons are moving back and forth. Okay, here they are oscillating back and forth, and here there is a collision zone due to repulsion. So the electron is like that, back and forth. Okay, and now you can. I extended it to many electrons. Okay, this is first time I know really this is 3 electrons, which are this lithium atom, and they are also doing the same. They are, each electron is oscillating back and forth. This is for 3 electrons, okay? And now, this is what happens if they are not, the initial conditions are not prepared precisely for these Click-Clack oscillations. Okay, and now also this is for 4 electrons that Z equal 4. This is for beryllium atom, for example, or this can be quantum dot also, which is doped with the charge, effective charge. Quantum dots are doped with effective charge, so the effective charge, doping effective charge, the Coulomb potential can be fractional. Okay, so this is the movie which is explaining all the previous. You see trajectories starting from here. If you see the movie, something was not clear, that you can see that they are preserving the square shape. They are on square, and the square is the plane of the square is oscillating, that the nucleus is passing through. Okay, like through the Stargate. There's a movie Stargate. So the electrons, nucleus. You can also do it with the finite mass nucleus, but I'm here. We have in the models when we assume that nuclear mass is infinite, simply, and this is a source of the Coulomb potential only. We don't include to dynamics. Okay, and there is a simple hardware model of this, that simply the electron is moving on a half circle and is bouncing through the rigid wall. And the packet, of course, this packet are not fully shape invariant. They are with this configuration, they are slightly changing shape. Okay, this is also electric field. Here is in linear polarization along the wall, and it can be decomposed onto 2 counter-rotating circularly polarized fields. So each of the component is in the proper motion, is in something similar to rotating wave approximation, is coupling to the motion of the electron. Okay. This is basically model for 2 electrons for the original Langmuir, but this is more, the models for n electrons is obviously similar. Okay, and now let me go to the point, the multi-layer Polaronic. This is the point, the title of my talk, and the main point of this talk is that we now find a very difficult trajectories which are multi-layer. So actually the oscillations can be by bouncing. This is 2-layer configuration. Okay, in the quantum dot, the quantum dot is helping the stability, because without any fields, those trajectories are normally unstable. Okay, and without CP field and without magnetic field, and this is also, we can add this is configuration in the quantum dot, in the spherical quantum dot. So you have here 6 electrons, and they are oscillating up and down. Okay, and to be clear, here again. Here is the case when you don't prepare the initial condition precisely, of course. So I was talking about it in the simpler case before, when they were not multi-layer. Okay, this is multi-layer configuration. So the electrons will up and down, and they are bouncing from each other on repulsion symmetrically. Okay. So this is very good. These are also very good solutions to check the quality of the solvers, of the classical solvers. Because if you, for example, if you put an electrons, if each electron is propagating the same trajectory from symmetry, because if solver fails on something, the classical equation of motion solver to fails on something, they will scramble that each electron will finally move different trajectory. Okay, but theoretically they should always preserve the same trajectory. Okay, and now to be more clear, okay, this is when you focus them. Okay, these are the Click-Clack Bose trajectories for 6 electrons. When you focus the initial conditions properly, Okay, this is quantum dot for Z equal 3 for lithium, or quantum dot with lithium core on the or effective potential Z if scaled, because you can scale this also. And this is omega of the in units when you have one solution, and then you can scale this also, because it's classical mechanics scales and quantum doesn't. That's a funny thing. It's, okay, and quantum mechanics only scales about the centers of the wave packets, but they are they if you consider circular motion, for example, of the Trojan wave packet at the beginning, that the ratio between the size of the packet to the radius of the circular motion is finally going to zero when you go to frequency to zero. So classical mechanics doesn't, quantum mechanics doesn't scale, and classical mechanics scales simply by you can knowing one solution, you can precisely find the other solution by scaling the parameters. Okay. And now to be more clear, you see the movie, the movie, how they are moving. So these are very difficult trajectories to find and to prepare. And I call them also Click-Clack. There's a multiple Click-Clack balls, like multiple Click-Clack balls trajectories. So I think only a robot could operate many Click-Clack balls, for example, already without the slices or surfaces. I think a robot programmed properly would do that. Okay, so you see again they are executing the Click-Clack balls motion, and there are 6 electrons. Each 3 electrons is in one slice, because there is a width of the motion. Okay, so now of course each trajectory show me that these trajectories are each electron, if considered quantum mechanically, is simply a cloud of the probability around it, and that's why this is the volumetric plot of the wave function, which resembles Trojan wave packet for each electron, even in the classical mean in the harmonic approximation. You consider the mean field from other electrons and expand the potential, and it is Trojan-like wave packet. Okay, so let me, since it's 25 minutes already, I think. Let me summarize this presentation. In 1921, using Langmuir in early attempts of the quantization of the helium atom by the Bohr-Sommerfeld conditions, found a periodic planar two semicircular like two electron classical trajectories corresponding qualitatively to the popular toy, the Click-Clack balls. We previously found that the trajectories can be extended to an electron atoms when the electrons collectively repeat the potential assisted symmetric collision event up and down twice a period, and they correspond to the hypothetical multiple Click-Clack balls operated by the robot, presumably human cannot do, or very trained human can. But here we find that such trajectories can also exist into multi-layer configuration, and the electrons in one layer oscillate synchronously on the fractions of the semicircles while exchanging the energy with other electrons in the collision analogy to polarons or plasmons in the cones matter, and the external oscillating electric field and the magnetic field in the direction of the disk rotational symmetry axis are stabilizing the motion, while the magnetic field is causing the rotation of the whole configuration at the rotational symmetry axis with the half of the cyclical frequency. And such trajectories can support the stable non-dispersing two-electron wave packets with the probability density solitons moving along the trajectories with some shape oscillations while periodically colliding with reshaping. And they can be confirmed in the Hartree-Fock 3D grid simulations in the Hartree limit, as well as within the stationary and now recently developed new time-dependent quantum diffusion Monte Carlo method. I developed the extension of the stationary quantum diffusion Monte Carlo method, when you can actually solve the time-dependent Schrödinger equation for large number of electrons, and it also can be observed. Okay, that I will conclude here.